All right, so let's take a look at the sections on dimension and properties of dimension. All right, so let's go to the definition. Given V is a vector space and V1 through V2 is a basis of V, then the dimension of V is defined as the number of vectors in the basis. If V has no finite bases, we say that V is infinite dimensional. Now, this definition presumes that any basis has the same number of vectors, which is something that's proven in the chapter. But any basis of a vector space will have the same number of vectors, and that number of vectors is equal to the dimension of the vector space. All right, now, if I have t vectors that span a vector space, then any set of t plus one or more vectors from V is linearly dependent. So if I have a set that spans and I add another vector to it, then that larger set of vectors is going to be linearly dependent. So in fact, if I have a basis spans a vector space, I can't add any more vectors to the basis and still have a linearly independent set. So you can say basis is the largest possible linear independent set in a vector space. Now, there's more than one basis for vector spaces, but each basis cannot be made larger and still be linearly independent. All right, so let's use some of these ideas to do some examples. So dimension of Cm is m, dimension of Pn is n plus 1, and dimension of Mn is Mn. So here's an exercise. I invite you to pause the video and try this. Give bases of C2, P3, and M23. All right, so if you tried this exercise, a basis of C2 would be 1001. That's actually called the standard basis. Basis of P3 would be 1x x squared x cubed, and you could also call that a standard basis. Here's another example of a basis. Make it bigger. Whoops, sorry. 1x x squared and x cubed. I'm sorry, that was one basis. Another basis would be 1 plus x plus x squared, 1 plus x squared plus x cubed. Now, you can see that this will span, and you can also see that it's linearly independent using arguments similar to arguments we've used previously in previous videos. If you try to form a linear combination of these polynomials, the only way to make that linear combination be 0 is if all the coefficients are 0. Right? And the basis for M23 is just set one entry at a time equal to 1 and all the others 0. So you can see there's 6 different matrices that we obtain that way, which form a basis of M23. All right. Now, dimension of nullity and rank. Nullity is just the dimension of the null space of a matrix, and the rank is the dimension of the column space of a matrix. Now, we know a bunch of things about rank. Dimension of the column space is also equal to the dimension of the row space. It's also equal to the number of linearly independent rows or number of linearly independent columns. So rank has several meanings. All right. And here's another important fact. Let R be the number of pivot columns. Then R of A is equal to R. N of A equals N minus R. And R of A plus N of A equals N. In other words, the rank of A plus the nullity of A is equal to the number of columns of A. Okay, so you can also say that the rank of A is the number of pivot columns, and the nullity of A is the number of free variable columns. It's also useful to know the number of pivot rows is equal to the number of pivot columns. And that's because each pivot column has a 1 in it, and that also marks a pivot row. Okay. So here's some examples that you should try. A 5 by 5 matrix has 3 pivot columns. What is R of A and N of A? See if you can come up with the answer. A 3 by 4 matrix B has linearly independent rows. What is R of B and N of B? A matrix A has 5 rows and 7 columns. The RAF of A has 3 zero rows. What is R of A and N of A? So you can pause the video, and then I'll give the answer. Okay. In this case, it would be R equals 3 and N equals 2. In this case, it would be, let's see, it's going to be R equals 3, N equals 1. And in this case, it's going to be, let's see, it's going to be R equals 2, and N is equal to, let's see, how many columns altogether? N equals 5. I see here when I say N, I mean the nullity, not the number of columns. Right, so those are the answers for those exercises. All right, here's an example from the book. It's problem C21 from the dimension section. It says, find the dimension of the subspace determined by this relation. So my hint is you can write W as the span of a set of vectors and verify that the vectors are linearly independent. All right, so I suggest you pause the video, try to do this, and I'll give the answer. All right, so to do this, we can write this as a linear combination. Now notice you've got unknown variables A, B, C, and D. I can pull out the A part, the B part, the C part, and the D part. So I can write this as A times 1, 1, 1, 0 plus B times 1, 0, 0, 0 plus C times 0, 1, 0, 0 plus D times 0, 0, 1, 1. Okay, so I can see that W is equal to the span of these 4 vectors, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 1. All right. Now, question is, are these vectors linearly independent? I need that in order to show that this is a basis. Okay. These vectors are linearly independent because set the linear combination equal to 0. If I set the linear combination equal to 0, think about what happens with the last component. The last component tells me that D equals 0, right? Because here I get A times 0 plus B times 0 plus C times 0 plus D is going to be equal to 0. So that means then the third component will then give me A plus D equals 0, but D is already 0, so A must be 0. Once you have D equals 0, A equals 0, then the second component will tell me that, let's see, second component tells me that C equals 0, and then the first component tells me that A equals 0. I'm sorry, not B equals 0, sorry. B equals 0. All right, so I can read off that these are a basis. So the basis is just this set up here. I'm lazy, so I'm not going to draw it again. The basis is just this set up here. Okay. All right, let's move on. Find the dimension of a null space. So here I have M22, and I'm looking for the dimension of this subspace determined by these relations. It's A, B, C, D, where you have these 3 relations. So I suggest you pause the video, don't look at my solution, pause the video, see if you can solve this on your own. Find the dimension of this subspace. All right, well, let me go through my solution. Let's rewrite these conditions as homogeneous equations. All right, so I just pulled the c to the other side. I got a plus b minus c equals 0 from the first, b plus c minus d equals 0 from the second, c plus d minus a equals 0 from the third. I can write that as a matrix. The coefficient matrix is here. I'm looking for the null space of this matrix. Okay. Now I know that the null space of A, the nullity of A, is the dimension of the null space, plus the rank of A must be equal to the number of columns. The other way of saying that is saying that the nullity of A is equal to the number of columns minus the rank of A. Number of columns is 4, so the nullity of A is equal to 4 minus the number of linearly independent rows. So let's go ahead and row reduce. If you row reduce, you can see that all of these rows are linearly independent. Okay. And you can use this same type of argument that they're linearly independent, because if you try to make a linear combination equal to 0, you get A equals 0, B equals 0, C equals 0. Okay. So that means the rank of A equals 3, so that means that the nullity of A must be equal to 1. Okay. And that's the answer. I think that's all they asked for. Find the dimension. So the dimension is equal to the nullity of this matrix. The nullity of this matrix is equal to 1. Let me see if I said anything else down here. Okay. Okay. So another way of saying this is that there's only one free variable. If the free variable is d, that means W can be expressed as d times a 2 by 2 matrix. So W has dimension 1. All right. And I think there's another problem down here we can look at. So here's a similar problem. I'll let you look at this yourself. This is in the notes, but it's a similar type problem. Right. Some more exercises. Find the rank and nullity of a matrix A. Remember, rank is number of linearly independent rows. Nullity is number of free variable columns. So if you REF, you get this. And you can see from here what's the number of linearly independent rows or number of linearly independent columns, and you can find the number of free variables. And remember that the rank plus n will be equal to 5. So I think you can do this exercise yourself. All right, so let's go over these concepts here. Let S be a set of m vectors in a vector space V with dimension t. What can we say about S? If m is greater than t, then S is linearly dependent. So if I have more vectors than the dimension, then those vectors must be linearly dependent. There are too many of them. If m is less than t, then S does not span V. In other words, if I have fewer vectors than the dimension, then those vectors cannot possibly span the vector space. So I have few vectors. So if m equals t and S is linearly independent, then S spans V. Okay. So if I have a vector space with dimension t, and I have t vectors that are linearly independent, those t linearly independent vectors do form a basis for the vector space. On the other hand, if I have t vectors and they span V, then those vectors must be linearly independent. Okay, so linearly independent set of vectors, and the number of vectors is equal to the dimension, is a basis. And if I have a number of vectors equal to the dimension and they span S, then that must be a basis. Okay, so here's an exercise. What can you conclude about the linear dependence and span of the following sets? A set of 5 vectors in C3, a set of 4 vectors in P4, a set of 6 linearly independent vectors in M23. So I'll pause the video, see what you come up with, see if you can get some answers here, and I'll tell you what the answers are. All right, 5 vectors in C3 must be linearly dependent, and you don't know whether or not they span, so they may or may not span. For example, suppose those 5 vectors are just simply 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0, 5, 0, 0. Those are 5 vectors, and they're certainly linearly dependent, but they do not span C3. Okay. A set of 4 vectors in P4, so in this case, I don't know whether it's linearly, so this may be, it may be linearly independent or linearly dependent because there are few enough vectors so they could be linearly independent. But I don't know. They might possibly be linearly dependent. And I can say they do not span P4 because there aren't enough of them. All right, now the last one, 6 linearly independent vectors in M23. Since 6 is the dimension of M23, these must be linearly, they are linearly independent because it says so, and they span M23. Okay, so that's it.